Welcome everyone to this short video, which is supposed to be a tutorial for this brief code that I wrote. And this code simulates the motion of a mass attached with the spring to a horizontal fixed surface. And the mass can oscillate vertically, that is up and down. And so this is a mechanical system with 1 degree of freedom. And once you write the dynamics, well, you'll find a second-order ordinary differential equation that describes the dynamics. So we're dealing with the second-order system. All right, so the first part of the code between line 5 and 30 is something that you can edit. That is the editable section of the script. And then we'll go into detail. Then the next part is just the numerical integration of the differential equations. The third part is just plots things, as you will see. And the fourth part, at the end, I wrote down the equations of motion. So you have the chance of setting up a few parameters for the system. In particular, you can set up the natural frequency at line 9, the damping ratio at line 10, and the mass value in kilograms at line 11. Then you can set up some parameters for the external force. You can choose between 3 forces, as you will see shortly after. So you can set up the amplitude of the force and the frequency if the force is chosen to be harmonic. We haven't seen harmonic inputs or harmonic external forces yet, so don't worry about line 15 yet. Then you can set up initial conditions for the mass in terms of initial position, line 18, and initial velocity. You can just leave these to 0. That is totally fine. And then you can set up the integration times on line 22. In this case, it goes from 0 to 10 seconds. And then you can choose between the type of driving force or external force. So what you can do is you can uncomment the force that you're interested in. For instance, if line 25 is uncommented, we are exciting the mass using an impulse, an impulsive kind of force. And then you'll have to comment lines 26 and 27. If instead you wanted a constant force, that is a step input, then all you have to do is to comment out line 26 and keep 25 and 27 commented. So on and so forth. Finally, the last thing that you can use or you can select is whether to have the animation on or off. I recommend that you just keep it on so you can see actually the movement of the mass. So let's take a look at some results of these simulations. Let's start by considering an impulsive force and an undamped system. That is, we should set the damping ratio to 0. So here we have an impulsive force, but the amplitude of this impulse is 20. So normally we've considered the impulsive force as delta of t, or the Dirac function, which has amplitude equals to, or strength, I should say, because the amplitude is technically infinite, but the strength is equal to 1. Now, setting up F naught, like in this case, to 20, well, it means that we're using an impulsive force 20 times as strong. All right, so all we need to do now is just click the run button. And you can see that the mass starts oscillating up and down. And since the system is undamped, it will just the mass will oscillate vertically indefinitely between a minimum and a maximum. If now we introduce some damping, let's say we set the damping ratio to 0.2, then the oscillation of the mass is damped and it will reach asymptotically the final value of 0. Here I've kept both plots of the position of the mass for the undamped and for the underdamped case. Finally, let's see the case for the damped, overdamped system. Let's set, for instance, the damping ratio to 2. And once we run the simulation, you'll see that the mass will reach the maximum or maximum negative or position, and then it will slowly reach or go back to 0. And this is exactly what we were expecting. These plots, which I should describe, it's the second subplot of figure 2, describes the position of the mass, is what was shown to you in lecture 5. The other two subplots of figure 2 represent, well, subplot number 1 is the external force. So in this case, we have an impulse at t equals 0 of strength 20, and then the force is simply equal to 0. The third subplot is the velocity of the mass as a function of time. Okay, so now let's change the nature of our input, and we switch from an impulse to a constant force, that is a step input. What is the amplitude of the input? Well, you define it using the line number 14. So in this case, we have a step input of amplitude 20. Let's start once again by considering the undamped case, and let's run the simulation. You'll see that the mass starts at 0, and then it reaches a maximum, and then it keeps oscillating between 0 and this maximum value. If you go back to the notes, you'll see that what we've considered was the oscillation between 0 and 2. So why is this maximum not 2? Well, that is because it was just a particular system. Here we're using different numbers. How do you find the maximum? Well, the maximum is 2 times, for the undamped system, it's 2 times f naught divided by omega n squared. And you see that this is 4.44 meters, and that's exactly the maximum of this, or maximum value for this harmonic force, about 4.4. All right, now let's introduce once again some damping. Let's set it once again to 0.2. And you'll see that the mass will reach a final steady state value. So what's the value here? Well, that's exactly a half of what I showed you earlier. So it's simply f naught equals, divided by the natural frequency squared. So 2.22 in this case. I forgot to keep the plots together. So let's do it so you can see all of them. All right. So finally, let's set the damping ratio to 2 in order to have an overdamped system. And let's see the simulation. So the mass now slowly reaches the final value without ever crossing it. So there's no oscillation for an overdamped case. Okay, so just have fun with this code. You're obviously free to use it, to edit it, to do whatever you want with it. Of course, if you use it externally of UCI, just please mention where you got it from. All right, that's it, and have a great weekend. Take care.